And essentially, this talk is, by its core, it's trying to be answer the question is, we're only looking at the possibility to use the AGL with the RT patch, real-time patch, and understanding that, when we, run the, safety application on top of RT Linux, essentially we need understanding, the underneath, right, the OS native, OS primitive kind of the performance in terms of what is the worst case execution time. So this is part of, I think it's for, if you go with, if you, for this, safety, standard, right, one of the evidence you need provide to the safety standards such as ISO 26262 is you need to provide evidence in terms of doing the dynamic time analysis to provide this kind of data evidence. So my talk is try to be have this unified the benchmark the framework, and it's meant to be work with any kind of POSIX compatible RTOS, including Linux RT. For the first a few pages, essentially set up a little bit context, right? Because, in terms of why we want to do that, right? Because of open source become a viable kind of a the alternative to microkernel based safety OS. So this is kind of a little bit context. I think my audience, much better than me, right? Essentially, what is the physical constraint, right? In terms of how we need the OS and also safety application to essentially to address any external physical events, right? Then provide kind of fast enough to response. Then take action within safety guarantee, provide a safety guarantee. And but think about this, right? The underneath hardware, modern kind of days, the hardware SoC becomes so complex. Essentially, a lot of non-deterministic behavior, such as the pipeline, the cache effect, and also the dynamic, dynamic interconnect across different IP blocks, right? Essentially, bring a lot of uncertainty, right, to interfere the safety application. So this is one aspect, coming from underneath, the high performance SoC, and also second source of interference coming from OS, your OS, right, such as Linux RT. There is also even the Linux RT patches try its best to make it hard, deterministic, but it still there is certain non-preemptible path. Essentially, you cannot kind of preempt. So this is just explain a little bit about a worst case execution time and why it matters, from the safety certification kind of perspective, and so this is I think I'm going to skip this slide. This is more kind of it's familiar most of kind of our automotive experts here. And I want to be just a little bit emphasize, what is this unified the work I present here, right? What are we trying to do? Essentially, we would try to be using this unified benchmark, right, to provide empirical benchmark the data. Essentially, fills the AGL-RT worst case execution time evidence gap. So this is essentially what we try to do. So this is A. Provide kind of a measurement in terms of what is kind of a worst case execution time in terms of multiple kind of OS primitives. This is A, B, and also we go further, right? We want to be understanding what is the root cause of those outliers, right? Is it because of underneath SOC kind of hardware events, interference, or it is because of underneath kind of OS, right, interference? So this is something we're going to be, essentially go further, not just kind of measurement results. We're going to answer the root cause of those outliers, and also provide kind of proposed countermeasure. So this is, I want to recap, right, a little bit kind of open source cyclictest, right? So this is essentially our inspiration, right? Our work is somehow inspired by cyclictest in overall kind of design concept, right? The cyclictest is essentially allowing you to really kind of profiling, kind of task switching kind of latencies, and allowing you to regulate the running time, such as CPU pinning, and also allowing you to pre-fault the memory, etc., to avoid runtime page fault, which is essentially introduce a noise. And so we're also using stress NG essentially to simulate the noise neighbor, right? Because you have the separate application, right? So maybe hosting kind of tier, right? The separate application. But at the same time, you have your noise neighbor. Say, for example, you have an entertainment system. Infotainment system is running. Besides you, maybe on top of the same SoC, where you have the SoC being partitioned, right, into the multiple virtual machine, right, side by side. How we're going to be emulate those noise neighbor, right? So we're going to use the stress NG, right, to emulate those noise neighbor to generate some, for example, CPU intensive or memory intensive or interrupt storming kind of situation, or a combination, right? Essentially allowing us, right, to generate a different recipe of the stress. So this is about a little bit kind of recap in terms of the background, context, right? Our inspiration from the cyclictest. For next few slides, essentially highlight some of the features and what it are capability, what we have been developed, these unified RT benchmark framework features. Essentially, we focus on portability, right? Because as I mentioned, right, it's meant to be not just Linux RT. It's meant to be, can be cross-compiled, right? Deployed on different POSIX RTOS, so which allowing us, right, to have a reference, right, cross wide kind of selection of RTOS to give us some reference, so we can learn from each other's different design. And the second thing is, just like what is cyclictest, right? We go a little bit step further. Essentially, we want to be normalized build time and runtime constraints, right? Essentially, because if you want to compare, right, the different kind of RTOS, right? You want to be essentially have a constrained kind of environment, right? So you can compare the results. So this is essentially we want to be doing. We're going to have that feature, and of course there's something like similar to a cyclictest, right? CPU pinning, memory locking, etc. And also something like we're going to be keep cache state consistent across each test run, because we're going to do a configurable multiple iteration of a test run to get a statistic test results. And also expectation is we have a built-in kind of a set of metrics we're going to be to benchmark, but the framework mean to be easy to extend. So this is the first kind of design kind of the goal. The second design goal is we also want to go beyond, right, to get the results, right? Identify what is the worst case execution time. We also need to understand root cause it, right? And essentially, we leveraging ARM in the performance counter to essentially allowing us to pinpoint, right, is it this outlier latency is due to contributed by the hardware events noise, right? So this is one techniques we're using. The second technique is essentially because other than the hardware events, right, the potential OS kind of noise potential kind of contribute to latency we're observing. We're using essentially kernel f-trace to give us kind of allowing us to pinpoint, right? Essentially, whenever that outlier happening, we want to see what is underneath kind of the kernel events happening. Right? Is it something like, say, interprocessor interrupt happening, or it's because some raw spin lock being held? So this is the second design goal, right? And to summarize, the two design goals. One is portability and also a regulated, normalized kind of runtime, build time. Second design goal is root cause analysis and pinpoint. It's not just guesswork. We're going to pinpoint whenever the outlier happening. We're going to understanding what is a pinpoint. Either it's a hardware noise or kernel kind of the noise. So this is a kind of a framework architect Lei Zhou overview, and I'm going to be so most left side is it's a built-in kind of the matrix, 5 matrix basic matrix. We're going to collect it's task switching and task preemption and interrupt handling latency, and also mutex shuffling latencies, and also the intertext message latencies. And we have a stress ledger, which essentially kind of generate a different combination of stress to simulate the noise neighbor to the safe application, and also some other kind of important kind of techniques we're using, and how do we present the final data in a P29, P39, and worst case. I'm going to skip this slide. This is just kind of illustrate, what is trying to get aligned with you, right? Which specific each of OS primitive essentially we try to be profiling. And this is give is essentially it's a recap, right? How going to be generate different the stress using the stress ng, the different kind of switch, so you can cook up, right, the recipe of the different kind of load. And as I mentioned, part of the features I think for this unified benchmark is across across different RTOS, right? We want to be normalized build time and runtime, essentially to build a kind of comparable environment, allowing us, right, to how to say, something like build time control is comply flags, right, and also memory lock call, and also disable the runtime voltage, frequency, scaling, etc. And the runtime control such as CPU pinning and IRQ affinity, etc. And also RT throttling. So by doing all this regulation, we're going to have create a clean state. So we're going to focus on OS primitive kind of the performance on the noise neighbor. Focus on that instead of being influenced by all these variables. So this variable will be kind of excluded. So this slide essentially, I think it's just kind of different command, right? Essentially, we're using, right, to regulate kind of runtime the behavior. Next few slides essentially it illustrated some of the actual kind of data sampling from the different OS. One of OS is ATR RT, and this is for task switch latency. And under different stress, right, is idle stresses and balanced. Balanced meaning it's a balance across either IOs intensive, between IO intensive, CPU intensive, and also interrupt storming, etc. This combination. And also there is a higher kind of interrupt kind of the stresses. In each the stress case, how task switching the latency behave, right? You can see that that the purple is essentially representing kind of a worst case execution time for the Linux RT is somewhere like 150 microsecond, and also it's showing the medium latencies, right? This is side by side, right? Essentially give you a comparison. So this is slide is actual kind of data collection, right? Coming from the actual kind of experiment, and this is for mutex shuffling latencies. It's what is the worst case execution time, the behavior under different stressor, and it's comparison between different POSIX-OS and AGL RT and another kind of microkernel OS. You see there is a big difference in terms of runtime performance. And this is for another kind of OS primitive, right? The task preemption kind of latency. And this is kind of interrupt handle latencies from whenever we're using GPIO kind of loopback, whenever GPIO kind of assert and the bottom half kicks in, right, consuming that, processing that event, right? So this is essentially we are to compute, capture the delta between these two events, right? And you can see, right, this worst case kind of execution time is in the IO storming case, interrupt storming case, stressor case, is somewhere goes to 157 microseconds. Last one is essentially some messaging latency, right? There is comparison between side by side, right? And the left side essentially it's a comparison between Linux RT and the microkernel OS, but both using the POSIX pipe. You see, interestingly, the microkernel OS, the case seems higher, right? But we need to realize that we're using kind of POSIX API, which is introduced kind of overhead, right? But if we using kind of native message API, right, then you can see, right, essentially microkernel OS, the messaging performance is much better, right? So this is just give you kind of more intuition. And the next a few slides essentially try to put in all those kind of actual kind of test data in different perspectives. Right? This is kind of heat map in terms of different kind of OS matrix, right? And on the different kind of stressing kind of loads, and side by side, between Linux RT and micro OS, the behavior. Like I mentioned earlier, right? Because we're not just going to be collect the benchmark, and we also need to understanding what is the root cause, right? Is it because hardware kind of noise, or is it because OS kind of noise, right? We need to understand, right? Before we get there, we need to understand what are the potential kind of interference, right? Kind of could be coming from, right? Because, say, for example, right, if there is a CPU stressor, right? So essentially, potential kind of interference channel could be a schedule preemption and cache contention, right, on the hot path. In the case of memory pressure in the kind of noise neighbor, it could be kind of something like last level cache eviction and also TIB pressure, right? So this is kind of a noise. interference could be kicked in, right, to our safety application, etc. And in the case of the block I/O load, potentially you're going to see some, XI bus contention or DMA interrupt storming, right? That kind of interference kind of attacking your, causing kind of interference in your safety application, etc. So this is kind of theoretically potential, right? For each this different type of stress, potentially, what kind of interference could be introduced to the safety application. But this is theoretical, right? And we need a way, in our case, to really pinpoint, right? We never, as I mentioned, as I illustrated earlier, right? So all those outlier kind of latency, right? Over, say, 500 kind of iteration, right? We need methodology, essentially kind of pinpoint, whenever there's outlier happening, right? What is ARM performance counter, right? What is a set of the kernel in a kind of execution kind of function when that outlier happening, right? We need a methodology, essentially kind of allowing us to pinpoint. So this is a few slides. It's essentially trying to answer that question. And so first one is ARM kind of performance counter correlation, right? Essentially, during kind of in our test framework, essentially whenever we capturing the data between context between when we capture kind of different kind of latency, right? We also capture kind of a performance counter before and after that outlier happening. Then we kind of whenever we finish this 4,000 iteration, we're going to have a snapshot of the performance counter, right? And then we do the post process. Essentially, we get a set of kind of data sets between outlier, either it's 150 microsecond for test switching, then pinpoint to say, this is last level cache missing, right? So this is kind of data set mapping. We're going to finally, going to be, provided by this framework. And so this is for PMU correlation. So this is the diagram. So essentially, it's only highlight kind of this PMU kind of correlation for the test switching case. I did not kind of provide all these kind of 5 matrix kind of the same same mapping between outlier to the 5 to the different kind of hardware performance counters, right? The correlation. Just give you example. So you can see, right, from this diagram, there is if you look at it, the data something like 1.x times, meaning that this is something can ignore, right? Meaning that because that number it's enrichment ratio, right? It's outlier counter value divided by nominal counter value, right? If anything higher than 1, meaning that the performance counter is become elevated, right, during the outliers kind of event happening, right? So this is become kind of suspicious. But it doesn't necessarily mean that that's kind of root cause, right? We have the second tier of evaluation in terms of using the Spearman kind of R value to ranks correlation between latency and PMU events, right? So this is 2-tier kind of the filters which allowing us, right, to pinpoint, is it exact this hardware kind of events causing this outlier, right? Either it's level 1 data cache refill, or level 2, or it's because of branch prediction, misprediction, etc. So this is essentially give an example, and in the case of test switching latency. So this is for PMU kind of a correlation, right? But it doesn't answer, say, if the outlier is caused by Linux kernel, right, interference, as I say, right? Even Linux kernel RT patch try its best to become preemptible as much as possible. But still, there's certain kind of path, right? It's not preemptible, such as raw spin lock, right? Whenever the scheduler, right, you do the counter switch, right? There's certain really fast, really short period of time, right? The scheduler, need to be essentially acquiring raw spin lock. So that's the time, it cannot be preempted. So this is also something we want to capture, right? As part of the unified benchmark and test framework. We want to be pinpoint whenever this outlier happening, then also do a post-processing, right? We're going to do the same timeline kind of caption over this, say 400 iteration, right? We're going to get snapshot and also timestamp. We're also going to be capturing a time-stamped kind of FTOS events over this 400 kind of iteration, right? Then we do the post-processing. So then we can understand, right, what is the outlier, say 150 microsecond. Is it pointing to, say, raw spin lock, or is it pointing something else? Or it's because of inter-processor interrupt, right? So this is essentially what we want to be looking at. So this slide essentially is give you an example, right? Is a test switching kind of the latency, right? Essentially, if you're looking at this looking at kind of the table, right? Underneath is essentially the primary kind of FTOS event when the outlier happening is when the scheduler, right, calling a raw spin lock, right? This is exact kind of a non-preemptible kernel path, right? Essentially, to delay the high priority task gets scheduled. So this is essentially so in this particular case, right, meaning that task switching kind of latency outlier is not essentially there's nothing we can. It's kind of architecture kind of ceiling. There's nothing. There's no single interrupt source is dominant, and this is so this is what's finding by doing this kind of pinpoint, right, and looking at FTOS. The finding is with maximum kind of Linux RT isolation, 99% of those outlier are kernel non-preemptible path, which is kind of Linux RT kind of ceiling, governed by the architecture. Okay, hold on. So this slide essentially kind of provide kind of this total of 5 metrics, like how we establish really root cause each outlier pinpointed a different kind of kernel noise, right, in each case. And the task switch latency, as I say, right, there's no software countermeasure can eliminate this path because it's essentially kind of governed by the the architect selection. And for the task preemption latency, right, this is essentially and it's also governed by the Linux its own architect. There's no configuration can eliminate the non-preemptible try to wake up kernel path. The third one is mutex latency, and the primary cause is last level cache kind of evasion, right? So this is essentially we have a countermeasure for it. Something like ARM kind of MPAM, or if MPAM is not supported right, on the ARM specs call, the cache coloring is the answer. And plus kind of IQ affinity, this is something we can apply. to really kind of allow us to countermeasure this root cause. Fourth one is interrupt handling latencies, right? This is primary kind of root cause is cross-process interrupt coming from, in case say memory management kind of subsystem potentially send kind of interprocessor kind of interrupt to invalidate kind of TLB, right? So this is something kind of coming from hardware kind of interference. So this is something can be countermeasured by the gig kind of IPI, software generate interrupt routing. Last one is intertask messaging kind of latency. Right? This is primary cause is last level cache eviction. And the countermeasure, as I mentioned, it can be MPAM or cache coloring. And so this is essentially kind of recap, and we understanding what are the worst case execution time for different kind of OS primitive, and then we have a methodology essentially pinpoint the outliers goes to either caused by hardware events or the kernel kind of non-preemptible the path, or a combination, right? Then we have some recipe, countermeasure recipe, right, to really, to fix or work around, those noise to improve. So I want to be kind of wrap up my presentation with some key takeaway, and the first one is essentially the worst case execution time, as you see, right, from the actual data, is greater than medium. And the second one is, microkernel S advantage for real. It's deliver 4 to 7 kind of times lower worst case execution time across all metrics on different kind of stresses. The gap essentially is architectural, not configuration dependent. And the third takeaway is the root cause is can be decided using the methodology essentially we are proposing, right? Using kind of give us kind of really using ARM kind of a performance counter plus kind of F-trace and plus post-processing allow us to really establish this root cause mapping. Last one, I think it's essentially what we are doing is essentially provide kind of a empirical kind of worst case execution time data is really valuable in terms of our safety certification as part of a dynamic timing analysis. So this is credits and contribution. This is part of one of the project we delivered for our customers. Part of a collaboration. I want to be thank you much. Sorry for kind of in the very beginning logistic problem, and appreciate kind of be patient. Yeah. Thank you much.
Questions? Really? Oh, wait, lots of questions.
Hold on. Microkernel S?
I don't think so, but I guess it's neutrino.
It's.
But you don't need to answer.
Yeah, yeah.
Can you repeat the question?
The question is, what is a micro S? Yeah, the micro S for us, right? Just we want to be, have a reference to understanding what is a position, right? When we evaluate this linear IT, right? Give a context for that purpose. Yeah.
Yeah. Okay. Thank you very much. And so actually, so I have two more questions. So do you? So I think so. Cyclic test or stress energy. So these are so stressors, and I guess so. You have some tools, and here my question is: do you open source your works?
Yeah, that's a really good question, right? So what we are doing. Oh, sorry. So what we are doing is, I think it's part of a multi-tier kind of a benchmark framework. Start from native right? RTOS.
Yeah.
Next, so this is something we're going to be, try to be, we're going to be plan to open source.
That's great.
Next tier is going to be virtualized environment, right? Either hypervisor based or hypervisor list based, because mixed reality deployment can be based upon hypervisor or maybe based on MP, right? You have a Cortex A clusters and also Cortex R cluster, right? You can deploy in that kind of setup. So we will only be covered in all these kind of situation. This is step one. We're going to do step two, hypervisor-based, and also hypervisor list-based kind of benchmark framework. So to answer your question.
Yeah. That's great. Thank you very much. And sorry, so I have one more question. So.
You used up your quality.
Yeah. Okay. Then later.
Jalen, did you have a question?
Okay. I see there's a red alert funding in your slides, and is that also telling us the Linux as a macro kernel operating system, it cannot be cannot achieve truly real time, because you see the spin lock is the architecture differences here, and the spin lock is being used everywhere for Linux open source software.
Raw spin lock.
Yeah, raw spin lock.
And the spin lock in Linux is preemptible. Raw spin lock is not preemptible. So there's difference. Yeah. So there's, as I said, right, the modern kind of Linux kernel RTE patches try its best to become preemptible anywhere, but it's a certain non-preemptible case, right, such as raw spin lock cannot be preemptible, unfortunately, for now. Linux, kind of a scheduler kind of a community is trying to work on it, right? You haven't kind of figured out a reasonable way to work around it. So this is essentially the architecture kind of ceiling. But that doesn't mean that it's going to be prevent, right? Linux RT be hosting the separate application, right? Because understanding this ceiling, we're going to understand, when we, plan the safety budget, right? We understand. Because it really depends on the safety budget, right? For the safety case, right? Say 20 milliseconds, right? So we know this architecture ceiling, so then we can budget properly. So this is essentially what I'm trying to say. It doesn't say, Linux RT cannot be, a real-time deterministic enough for self-caching.
Actually, the time tolerance window varies. If every kernel module requires abundant time budget, then it's never going to be enough time, real time.
I think it might be the angle, right? It really depends on how you're going to be understanding the angle. Right? It's only give you that kind of ceiling. That's important, understanding architecture ceiling. Right? That's the worst case. So then for the safety engineer, so they can budget properly. Right? So that's kind of key points, yeah.
All right, thank you, Lee.
Yeah, thanks, kind of, yeah.
So
Good question.
the schedule has not been adjusted online, so we'll come back at 4:15, okay? We are going to take a break now, and we'll come back at 4:15. Thank you.